Okay, so this will be the last video today, and I'm going to talk about some properties of networks. The main thing with this video is the concept of redundancy. And I mentioned that in the first video or another video today. So we're going to talk about some properties of networks and specifically redundancy. So let's talk about some properties in networks. In a network with n vertices and m edges, m is always going to be greater than or equal to n minus 1. Okay? So m is always going to be greater than or equal to n minus 1. That means that the number of edges is at least n minus 1. Okay? That's all that means. So in a network with n vertices and m edges, the number of edges is always going to be greater than or equal to the number of vertices minus 1. Okay? When m equals n minus 1, the network is a tree. So I drew a picture of a tree down here. So let's look at that. So remember, m is edges, and n stands for the vertices. So it says when the number of edges equals the number of vertices minus 1, the network is a tree. So here we have, in this picture, in this diagram, m is the number of edges. So there's 1, 2, 3, 4, 5, 6. And then there's 1, 2, 3, 4, 5, 6, 7. So notice that m equals n, which was 7 minus 1. So these two things are equal. That means it's a tree. When the number of edges is greater than n minus 1, the network, it's still a network, unless you have a graph that's not connected. But if the graph is connected and the number of edges is greater than the number of vertices minus 1, the network has circuits. So before I talk about the last part, let me draw a network that's not a tree, meaning that it has circuits. Hopefully I have enough room. I could even erase the top part, but I won't. Let's draw a network that has circuits. That's easy to do. I can just do this. Hopefully you can still see it. Can you see it? Yeah. So this is a connected graph. So it is a network. And I can tell it has circuits. So it's not a tree. Okay. So let's talk about number 3. The difference between the number of edges m and the minimum possible number of edges n minus 1 is called the redundancy of the network. In a network with n vertices and m edges, the redundancy R is given by R equals m minus n minus 1. Okay. Redundancy basically means that this graph has a certain amount of edges that don't really need to be there. You could take away a certain amount of edges and it would still be a network. And if you take away the right number of edges, it would be a tree. So basically that's what redundancy is. It's the number of edges that don't really need to be there. You could get rid of this many edges and it would still be a network and it would actually be a tree. So let's see what that is in this problem. Then I'll show you. Whatever we get to redundancy is, I'll take away that many edges and you'll see it's still a network. So R equals m. M is the number of edges. So we have 1, 2, 3, 4, 5, 6, 7, 8. I'm going to double check. I should label them, that way I know I'm right. We have 1, 2, 3, 4, 5. Right, I was right. There are 8 edges. So 8. How many vertices do we have? 1, 2, 3, 4, 5, 6. The redundancy in this network is 3. What that means is there are 3 edges in this network that can be removed, and it would still be a network. And it actually will wind up being a tree. Now, it doesn't mean there's 3 specific ones. There's probably more than one combination of 3 edges I could take away. But I'm going to look at the graph and see what I could take away. Well, this edge right here, I can take that away. The graph is still a connected graph. Okay? Same with this one. Graph is still a connected graph. And like I said, I think you could take, the next one that you could take away is any one of them. Like if I take away this one, the graph is still a connected graph. So I just took away 3, and the graph is still a network. That was because the redundancy was 3. I can't take away another one though. If I took away like this one, it would no longer be a network. So redundancy is the number of edges, extra edges basically. That graph to begin with had 1, 2, 3 edges that it really didn't need, and it still would have been a network without those 3 edges. So it's a network right now. But like I said, you can take away that edge, and any of the other edges. Doesn't matter, right? I'm going to just take away that edge. And it would still be a network. And now it's actually a tree because it has no redundancy now. Okay? And that's actually the next thing I'm going to talk about. And that will be the last thing that I talk about. Is when R equals 0, the network is a tree. When R is greater than 0, so like 1, 2, or 3, the network has the network is not a tree, so it has circuits. So we just saw in that graph that I drew that R was greater than 0. It was 3. So that network had circuits. Since R was 3, if we took away 3 edges, the network became a tree. So that's what redundancy is. It's basically the extra amount of edges that aren't really necessary for the graph to be a network. You've used the word redundancy probably either sarcastically or in other walks of life. Like, I used to work in telecommunications, and a lot of like I worked in basically things that were cell phone towers, and inside the we call them UCBs. I don't know if everybody calls them that. Unmanned communications building. Inside the building with all the telecommunications equipment, there were usually 3 or 4 of each. Like there's modems, multiplexers, things like that. Inside each building, there's usually more than one, because you want redundancy. That way if one breaks down, you can just use the other one. Or if somebody says something that means the same thing twice, you usually say sarcastically, oh, that was redundant. So yeah, things that aren't really necessary are redundant. So in a network, if you have extra edges that you don't need for it to be for it to still be a network. The number of edges that you really could get rid of for in a network would still be a network is called the level of redundancy. So we had, in the example I just drew, there were 3 edges that really didn't need to be there for the graph to be a network. So that, therefore, the graph or the network had a redundancy of 3.